Hello and welcome to another video by Adrian from Pure Electric. Please also take the time to watch the first video in this inspection testing series, which covers safe isolation, as you need to understand how to keep yourself safe before you start trying to move on to testing and installation. In that video, I explain why it is essential that we isolate before testing, along with the safe isolation procedure, and ultimately where to isolate and how. I also explain how safe isolation ties in with the Electricity at Work Regulations 1989, and a brief explanation of what happens when you create a short circuit, for example, whilst cutting a live cable and why your cutters blow up. This video is part 3 of my testing series for apprentices, where I talk you through my interpretation of how the MFT works before we move through the individual tests. I find that a lot of content that I watch shows you how to set the meter up and press the button, which is all well and good, but not so much of the theory and principles behind what we do as electricians, which I personally believe to be massively important to actually understanding the concept of testing. I'm hoping that this video series will not only help to keep people safe, but also to enable you to retain your new knowledge, as I believe that if we understand the knowledge, rather than just some facts we were told once upon a time, or in the worst instances, people performing monkey see, monkey do, then we are better equipped to deal with any situation using our engineering judgment. In fact, I would argue that incompetent testing is probably as, if not more dangerous than testing at all, especially as there may now be a potentially worthless certificate claiming the installation is safe, and also a good chance in this day and age that it has a competent person scheme logo, lulling people into a false sense of security when in fact it may not be further from the truth. Hopefully, with the help of this video, your testing ability will improve and you won't unintentionally become a part of the problem. Before we discuss the multifunction tester, we first need to understand what happens in a normal, healthy electrical circuit. Without voltage, the electrons are just floating randomly in a sea of electrons, moving around in different directions within the copper conductor. Here we have a basic illustration of a 230 volt AC circuit. AC stands for alternating current. When an electromotive force, measured in volts, is introduced to those electrons, the EMF will push them all in the same direction. At the bottom of the screen, I have drawn a very basic waveform and highlighted the top half of the waveform to represent the half of the cycle pushing the electrons. And without going off topic too much, all I want you to take away from this for now is that in an AC circuit, one half of the wave pushes the electrons one way, and then they flow back the other way, on the other half of the cycle. In the UK, we have a frequency of 50 Hertz, which means that this complete waveform happens 50 times a second. The other thing that you need to know is that when the electrons all move together in one direction, this is known as a charge. So how many electrons do we need to make 1 amp of current? An electrical charge is measured in coulombs after the French physicist Charles Coulomb. He determined that 1 coulomb of charge was equal to 6.24 times 10 to the power of 18, or the extremely large number on the screen. He also determined that if the drift of electrons was at a rate of 1 coulomb per second, as the second is the SI unit for time, then 1 coulomb per second would be equal to 1 ampere and the following formula: Q equals IT. Or current would be equal to 1 coulomb divided by time. So I equals coulombs divided by time. So how does all this relate to using a multifunction tester when testing R1 and R2 circuit resistances? Here is a quick recap on insulators and conductors. Copper is a really good conductor and electrons flow easily. So easily, in fact, that we need a way to contain those electrons and stop them from escaping. And we do that by surrounding the copper core with an insulating material, designed to prevent electrons escaping unless it is damaged, of course. You need to understand the difference between the two dead tests. Continuity in testing R1, R2 is checking for electron flowing easily and is usually carried out in series within the circuit. Remember, for the low ohm resistance test used for checking R1, R2 values, we are essentially proving that electrons can flow easily, and as such, the low resistances will be measured in ohms and milliohm increments. Most low resistance ohm testers measure in 10 milliohm increments, which is about 0.01 of an ohm. Table 41.3 in BS 7671 gives the maximum ZS resistances for protective devices to operate correctly in an earth fault condition. As the CPC is equal to or less than the neutral conductor, it is assumed that if the circuit fault path is satisfactory, then the neutral will also comply. Later in the series, when we get onto insulation resistance, we are testing the insulation between conductors. And as a result, this test will be performed in parallel, and that the electrons are contained and cannot escape. That test will be a high resistance test, usually at 500 volts, and with resistances at megohms, or millions of ohms. BS7671 gives a minimum installation value of 1 megohm or 1 million ohms, although on a new installation, guidance notes 3 suggests that anything less than 20 megohms should be investigated. The flow of all those electrons in a circuit is what powers the equipment and appliances that we have, and we as electricians need to prove that the electrons flow easily within the circuit with little restriction. Otherwise, we could end up with an overloaded circuit, where the cable gets too hot from all those electrons struggling to move in the circuit as quickly as they are required, and the worst case scenario is a fire. If you remember back to the first video in this series, the safe isolation video, you will know how dangerous it would be if we wanted to measure the flow of electrons in a live circuit. A circuit where there are potentially thousands of amps of current that we could connect ourselves to and have current flowing through us. I also showed you the effects of electricity on the body and how only 0.1 of an amp could stop your heart from beating, but you would need a higher voltage, around 50 volts or more, to really push that current through your body. So instead, what we do is look at the hierarchy of controls, and we can easily eliminate the dangerous 230 volts to 400 volts mains voltage, as that is the most effective way to deal with the hazard. But we do still need a voltage to create the EMF to move the electrons within the circuits. We can then substitute that dangerous mains voltage with that potential thousands of amps of current with our MFTs, which has a much safer voltage, around 4.4 volts of DC battery voltage instead, that only carries 200 milliamps of current. To start, I'm going to try and explain in a very basic way how the multifunction tester works, in order that whilst you are testing on site, it may help you picture what may be going on behind the scenes. If you can start to understand that, then the fault finding also becomes a lot easier later on. The following is my interpretation, and I hope it makes sense to you. Please also read the disclaimer, and that you read your MFT's user manual before you attempt to use it. When I was an apprentice, I bought myself a Mega 1552, which I found to be extremely easy to use due to the color coding and simple twist dial. I then upgraded to the 1553 with the Bluetooth connection, and the Bluetooth was a bit of a waste of time. However, in my opinion, the 1552 and 1553 were bulletproof and never let me down. In fact, I bought the 15.3 back in 2008-ish, and I still use it today. You can get one on eBay relatively cheap, and if I had another apprentice, it would be my go-to choice for them to learn. Later on, when I had a better understanding of testing, and I still had a couple of apprentices, I tried a few different manufacturers, but for me, nothing was as simple to use and demonstrate to the apprentices as the Mega, and for the purpose of this video, I'm going to be demonstrating the Mega MFT 1741. And as you can see, the same color coding and simple design has continued. This is the top of the range model, and there are simpler ones to use without all the features that you may not need. So how does the meter work? The batteries provide the electromotive force, the voltage, which the Mega MFT limits to 4.4 volts during the low ohm resistance test used for R1, R2, and this enables the current, aka the electrons, to flow. The Mega MFT limits the current flow from the batteries to at least 200 milliamps when measuring at 2 ohms, which is much lower current than the electrical supply to the property, but still enable those important electrons to flow. The MFT can then use these figures as a baseline from which to calculate our circuit resistance values. So the potential difference measured in volts provides the electromotive force, enables the electrons to flow around the circuit, and while the electrons are moving, the meter can measure the electrons flowing in that circuit and then applying Ohm's law to calculate the resistance. Interestingly, when performing insulation resistance, the MFT drops that current to around 1 milliamp when testing at 500 volts for safety reasons, as we are now over that 50 volt safe touch voltage. This means that you actually use the batteries up faster when performing low resistance tests because your MFT is using more electrons, therefore more battery power, while measuring R1 and R2 than you do when testing insulation resistance. Now, I want you to picture that electron flow in your mind when you are testing. When electrons flow easily, we get low values on the MFT, which is good for proving R1, R2 resistances, and the lower the better, as it means the electrons are traveling around the circuit with little restriction. As electrons become restricted, we start measuring higher resistance values. Later on in the series, we will also start to look at the fault current needed to trip an MCB, so you will start to understand why low resistances are critical to the circuit functioning correctly. So let's get started. In this section, we're going to look at testing between line and neutral with the MFT, which isn't traditionally carried out on site unless it is for ring final circuits, but we will get onto the ins and outs of that in a later video. The reason that I'm showing you this now is so that you can get an idea of those electrons flowing through a circuit in a normal, safe condition, where we want electron flow for a circuit to work. Then later on, once you have grasped a basic understanding of how that electron flow for a circuit works, we can then transfer this knowledge to the R1, R2 earth fault path. As we are talking about healthy, safe circuits, we can then discuss what a good reading actually is and what might be causing a bad reading, so that you can compare your results and fault find if need be. You need 2 leads for this test and to set your meter to ohms, which is color-coded orange on the Mega MFT. The dial to the right is not used for this test, so it doesn't matter where the dial is set to as long as it isn't on the spanner setting. It also doesn't matter what color lead you use, but to avoid confusion, I will be using a red and black lead in order that you don't get confused between testing values between line and neutral and line to earth when testing R1, R2 resistances. This may help you in the beginning too when connecting to a circuit, and when we are testing continuity, we are performing a low resistance test, so remember that we will be measuring in milliohms and ohms. If you look at the current display, anything to the left of the decimal point in this test will be ohms. Everything to the right will be in increments of 0.01 ohms or 10 milliohms. The continuity test is automatic on the Mega. The test starts as soon as the leads are connected to a circuit, and the test button is only used to null the lead set, which saves trying to find the test button when you're holding the probes in with both hands. In the practical classroom where I teach, the apprentices prefer using the Mega for that very reason and will wait until it's free rather than using another brand. This is the back of the Mega MFT 1741, and as you can see, the color coding continues. Because we are just dead testing resistance using a low ohm resistance test, all we need are the plus and minus terminals of the meter. They are also marked as L1 and L2 respectively when testing live circuits. Whichever way around you connect these for the low ohm resistance dead test isn't going to make any difference to the test that we are carrying out, and I will show you why. At college, we are taught that electron flow comes from the negative, so all that will happen is that the electrons will flow down whatever color lead you plug into the negative terminal and want to return back to the positive terminal, just like this. And for a really great video and other related content, I recommend watching and subscribing to Paul from the engineeringmindset.com, as this will help you with a lot of the knowledge required in your electrical course, as well as in this video series. The link to the video is on the screen. Terminal 3 is for balancing the RCD, for instance, when testing ZS, RCD trip times, when testing phase rotation, or performing earth rod testing. As such, this terminal won't be used in the low ohm resistance test for verifying R1, R2 resistance values. Make sure that the 4mm probes are fully inserted, and we can then prove the meter is working. It always amazes me how many people don't prove that their meter is working, that the leads are connected correctly, or even safe to use. If you do not do this, you may be testing, or lack of it, for a long time, or chasing faults that don't exist. The most important checks before you carry out any testing is, has the meter got sufficiently charged batteries? Are the leads undamaged and in good working order? If I'm live testing, are the leads GS38 compliant? Are the leads connected correctly? Does the meter work? And are the leads nulled? I tend to check most of these when starting each test to ensure that my meter hasn't developed a fault and that I haven't connected something up wrong, or I'm not about to make a silly mistake that is going to cause me to fail the assessment. To prove your meter is working, simply connect the probes together. If the leads are connected correctly and the dial is in the correct position, the meter will show a reading. If not, check your connections and the settings of your MFT dials. The movable jaws are only connected by a pin acting as a hinge, and are sprung loaded to produce the gripping power. As such, you want to ensure that the jaws of the test meter are connected with the solid jaws and that the main body of the test leads are in contact facing each other, as shown in the picture. The continuity test will also range from 0.01 ohms to 99.9 thousand ohms. Circuits up to 2 ohms will be tested at less than 200 milliamps, and once the display shows a value, it will automatically be logged into the temporary memory. Unless stored, this will be overwritten by the next measurement. On other multifunction testers, you may have to press and hold the test button. Short the probes together, press the test button, check for the null lead symbol. You should then check that your leads are correctly nulled by unconnecting the leads, and the meter should show an open circuit and continue to display the null symbol. Connect them back together again, and the circuit should close, the meter should read 0.00, and the null symbol will still be shown. If it doesn't read 0, put the leads back together again, press the test button once to unnull the leads, then once again to renull the leads. Then check them again by unconnecting and reconnect them as shown in the picture. We have nulled the leads and taken the resistance out in the same way that you would zero scales when measuring weight. It is imperative that you test and prove your meter before you begin testing for a number of reasons. Firstly, when you are starting out, it is a good way to remind yourself how the meter behaves and checking what you are looking for. Secondly, every assessor should be checking that you have set your meter up correctly. If you haven't proved this, you may fail an assessment. Thirdly, if you haven't checked your meter, how do you know your meter is even working or that you have connected it up correctly? You may be chasing that non-existent fault and wasting valuable time. All of this is what the assessment's about. Firstly, keeping people safe, and secondly, working efficiently so that you are not losing you, your employer, or the client money. Here are some possible errors for dead testing from the Mega user manual. So the presence of circuits connected in parallel would mean that you might get a lower reading than you should. You may even be getting a reading when you shouldn't, and we will discuss that in more depth in my next video on bonding. So ensure that you have disconnected your parallel ways. Presence of AC voltages in excess of 4 volts on the circuit being measured will prohibit the test. A poor connection to the circuit under test. This may be from your test probe or crocodile clamp not making sufficient contact with the circuit, or a loose connection somewhere. Incorrectly nulled test leads, which we have spoken about, and the use of fuse leads. Could add extra resistance into the circuit, or if the fuse blows, you could then have a lack of continuity. Now that we have spoken about why we need to dead test and the potential dangers of not carrying it out correctly or safely, we can now start to discuss what we should be looking for. For that, we need to know what a good low ohm resistance reading is or looks like. We are going to start by looking at testing between line and neutral in our circuits so that we can understand what we want to happen in a healthy circuit. Think back to when you checked your meter and leads, then nulled the resistance of the leads out. Notice when the leads are not connected and the circuit is open, we have no electron flow, so the MFT cannot calculate resistance. In this example, the meter is showing out of range on the screen, which on the Mega MFT 1741 is greater than 99.9 thousand ohms. When the leads are connected together and the circuit is closed, the electrons are able to flow, which means the meter can calculate resistance using Ohm's law. So which is good and which is bad? Well, that depends on what you want to happen, and I will cover this in more depth during the fault finding video. But for now, all you need to remember is that if you don't want electron flow, for instance, a light switch that is off, then a no continuity reading is good, as the circuit is functioning correctly. And when you connect your meter into the circuit, it will display as an out of range reading like this. If you do want electron flow, for instance, now that the light switch is on and we have a complete circuit to enable electron flow to power the light, then a low resistance continuity reading is good. As we have previously discussed, the batteries provide the potential difference in EMF to enable the electron flow, which I've shown with the arrows moving around the circuit. You will notice that the flow is coming from the negative terminal to represent electron flow in order to help you remember this for your science exam. In this illustration's most basic form, we have a sufficiently low reading. We have proved that the circuit is capable of electron flow, which means the circuit will work safely, and the light will illuminate when the circuit is energized. We have also proved functional switching of this circuit, as the light will be operated by the switch. Remember, if you want something to work electrically, then you need a complete circuit and for those electrons to flow. When you are testing the circuit and you are not getting a reading at all, when you know you should, That means the electrons are not flowing, and you must have an open circuit, also known as loss of continuity. The circuit is not continuous. To diagnose this, you need to test sections of the circuit until you find the break. In this example, in order to find this break in the circuit, we can test between the distribution board neutral bar and the neutral terminal at the light, which would show as an out of range reading on your MFT, signaling an open circuit and proving loss of continuity on the neutral. In the real world, you will probably need a wandering lead to be able to test between various points in the installation, which is effectively an extension lead for your test leads. The main reason people use these is to test bonding conductors from end to end, which we'll discuss in the next video. On your small practice assessment boards at college, testing continuity should be relatively easy, as your meter leads will probably be long enough to reach most points in the installation. As you can see from this picture, the meter is registering the resistance of the lead, but still displaying a null symbol in the top left of the display. Don't forget to re-null the added resistance from the wandering lead and zero your meter again. This is how you might use a long lead in this situation, but for the following examples, I'm going to leave the long lead out for clarity. If we then test each individual conductor on the neutral, we can then prove which leg of the circuit is causing the loss of continuity. For example, if we test the neutral conductor from the switch to the light, we can see that we have continuity, as the circuit is closed and the electrons are flowing really well. As a result, we have a low resistance, meaning that continuity and sufficient electron flow has been proved. At this point, it would be easy to assume that the fault is with the neutral supply into the switch, but as we should never assume anything in the electrical trade, we should always try to prove beyond all reasonable doubt that we are correct in our diagnosis, as mistakes can be costly, not only financially, not only with reputation, but with people's lives. If we now move on to testing the neutral supply into the switch, we can see that there is no continuity, as we have an out of range ohm reading on the meter, which proves there is no electron flow. At this point, there are no further connections in the circuit, so you need to assess the option. Is it a loose connection that needs tightening? Is it a misconnection and the neutral is connected into the wrong terminal? Is the neutral actually connected into the terminal? Or is there a break in the cable? Or is the cable damaged in some way? Are you even testing the right cable? We've all made mistakes, so we should always double, even triple check ourselves. Once we have found the fault, then we can repair it. And don't forget to retest the circuit with both the switch off, with no electron flow as expected, because the switch is off and the electrons cannot flow due to the open circuit, and now with the switch on. The electrons can flow, the meter can calculate that resistance. Because the circuit is so small on the page, the electrons are flowing really easily, and we have little resistance slowing the electrons down. And our meter registers that as a 0.3 ohm reading. In the real world, you will get varying resistances. The next few slides are to get you thinking about upstream and downstream, just like a river. The source of where the water comes from is upstream, and the river flows downstream to the end. Here is an example of a small circuit with 4 lamps. The light switches are excluded to simplify the circuit and help you visualize. First, we need to isolate the supply to the circuit, as you should not be trying to find faults with a live circuit. If you do not understand why, then again, watch the first video in this series on safe isolation, dangers of electricity, and how to comply with the Electricity at Work Regulations 1989. Once you have safely isolated the supply to the circuit, we then break that circuit down. You can start testing between the neutral conductors, either starting at the consumer unit end, if you have lost all your lights, as shown in this example, and by working your way downstream, from the MCB into the circuit until we find the break in the circuit, which could be either the feed out from the consumer unit to the first light as shown here, or the feed into the first light shown here. You would then repair the circuit and prove that it works with your multifunction tester before proceeding any further. If the circuit is now complete, the electrons would start to flow, and then the meter would display the resistance measured. In the next example, we have a partial loss, where the first 2 lights are working and the last 2 lights are not. You may decide that you want to start from the end of the circuit, the non-working lights, and work your way upstream to find the fault. Again, isolate the circuits first, and then work your way backwards upstream from the first light, which had a loss of supply, and find where the loss of connection has occurred, which may be the feed in from the last light that was working or the feed out. Again, you would then repair the circuit and prove that it works with your multifunction tester before proceeding any further. If the circuit is complete, the electrons would start to flow, and then the meter would display the resistance measured. Remember, As the circuit gets longer, there are more electrons that would have to move, which would add more resistance into the circuit, and that would slow the electron flow down. The result would be that the meter would start to record higher values at each of the points tested further within that circuit. As you can see from these two circuits, the bottom one is twice as long and there are twice as many electrons for the voltage to move. The top circuit has moved all of its electrons in half the time, so it has half the resistance, which we can now see represented on the MFT display screen. In the next video within this inspection and testing series, we will compare our results to the tables in the on-site guide and guidance notes 3, so that we can prove that our circuit resistance values are correct. Experience at testing on site will help you make these judgment calls using your engineering judgment. And this judgment will speed up your thought processes and enable you to get to the solutions quicker. You cannot rush experience, it takes time. And as a rule of thumb, I would estimate that even after you've qualified, you need at least 10 years experience in a huge variety of situations to really know your trade. And we've all heard people whose self-belief in themselves is off the chart. So I always remind myself of the Dunning-Kruger effect, which is the cognitive bias whereby people with low ability at a task overestimate their ability. So the next time you hear someone banging on about how much they know, or how good they are, or how easy electrical work is, then just picture this diagram and how they may be sitting on the top of Mount Stupid. And likewise, if you feel like you are in the pit of despair, then just remember that you are on your way to the slope of enlightenment. Some researchers also include in their definition the opposite effect for high performers, their tendency to underestimate their skills. But never forget that if you don't use your knowledge, you will lose it. Your brain is like a muscle. And if you don't exercise it regularly, in the same way an athlete would go to the gym, then your brain will trim off what it doesn't need. So continuing professional development is essential, or you will regularly hear it referred to as CPD. Finally, if you are not getting enough testing experience on site, then you need to have that discussion with your employer. It's no good relying on the small amount of time you spend at college. That time at college is precious, and you do not want to be spending that time learning how to test. You want to be spending it refining the knowledge that you already have learned at work from your mentor. As an example, in an apprenticeship, you might spend 80% of your time learning on the job, which is your 4 days a week at work. Your 1 day a week at college accounts for 15% of your time. And as the college are typically only open between 36 weeks for FE colleges and 40 weeks for private, that leaves between 8 to 12 additional days that you spend at work. And this is where some of that off-the-job training you have to log comes into play. But the good news is that you can fill that with CPD, as long as you are in your normal working paid hours. As an added bonus, things like this video series on testing count as CPD, as well as many of the other videos I have on YouTube. So get watching and get logging. And finally, thank you for watching. Please also look out for the next video in my inspection and testing series for electrical apprentices, where I talk you through R2 testing of the main earthing and bonding conductors. I hope you've enjoyed watching, and if you like this content and want to see more, then please like, share and subscribe to get these important messages out there so that everyone can benefit from them. If we all love, care and take individual responsibility for this industry, then our everyday world will be a much more positive place to be. Take care.